Good morning. Today we're going to be going over the walking cycle for SmallKat. Now in our last video, we started out by figuring out how to move the body of our robot by telling the tips of the legs to go to some new location. We applied the delta body to the pose of our robot and thereby computed where the tip needed to go. Alright, so now let's imagine we want to use that strategy to form a walking cycle. And that walking cycle would come out, up, back, down, and end right where it started. So let's see what that would look like. Alright. So, these are all the foot corners that we would want to form our walking cycle. We move back 3 times on the ground, up 1, and then reverse the direction of the body 4 times, then come down, moving back 1, 2, 3, and 4. In order to get our ratios lined up, each one of these green ones is going to represent 1/6 of the motion that we want the body to move, and each one of these yellow ones will represent 1/3. And so by doing that, we ensure that on opposite sides of the algorithm, the feet will always be on the ground. So that's why there's 3 intermediate points here to 1 intermediate point up here. The purpose of that is to ensure that the foot is still on the ground when the other set of feet are coming down and contacting the ground, so that there's a handoff at ground level. That's why we have them arranged like this. You'll also notice that if these are all proportions of the same frame transformation, these being 1/6 and these up here being 1/3, well, then that means the foot's going to be moving twice as fast along this upper section than as it will along this lower section down here. So, let's take a look at what that tip plan would look like. Alright. Now, you'll notice, first thing we do is we move by 1/6. And this 1/6 determines a scale of the delta that each one of these little increments represents. So T1 to 2, T2 to 3, and T3 to 4. So that's 1, 2, 3, and 4. Those all represent 1/6. Now, the 4 to 5, which goes up here, does the same delta on the motion of the foot, but it is also going to translate it in Z by our H value. So this is the same H value here, and then of course negative H down there. So, the foot comes back 1/6, 1/6, 1/6, 1/6, and then we flip the direction. This time the scale is double that, it's 1/3, and we're going to do the inverse of that motion to go back, back, back again. So this is going to move 5 to 6, boop, 6 to 7, up here, 7 to 8, over here, 8 to 9, over here. Those will all be the inverse. Alright, now, to come down, we start moving forwards again, because we're not exactly sure when the foot's going to contact the ground, but when it does, we do want it to be moving forward. So we're coming by our body delta, scaled by 1/6 again, and then this time we're going to translate down. And for the last 4, same as the first, last 3 is same as the first 3, back 10, 11, 12, and back to 1. Alright, so now we have our tip plan figured out. What do we do with that? Well, the next piece of the algorithm we're going to need is the math from last week. We're going to turn it into a function here. And this function is going to take in the body. We're going to take in the body, the specific leg that we're working on, the current pose that this leg would be in at the beginning of the translation. This isn't necessarily where the leg is now, but where it would be at the beginning of this motion. And the delta body we want to move this leg through. So, what do? We offset the starting pose, we apply the global delta, we compute a new tip, and we return the new tip. This should model exactly what you did last week. Now, how do we compute all those corners? Where are the tips for each of these legs? So the first thing you do to implement this function here is you're going to compute the foot home and apply any offsets here. Let's see what that looks like real quick. You're going to compute the foot home here. And then these would be the offsets. So let's say we want the leg to start a little bit down from where the calc home is. Remember, our calc home position is here. We're going to be down, and I think I'm going to move it a little bit forward. So to implement this algorithm and get it to walk really nicely, these starting points for the home work pretty much awesome. All right. So you apply any of the offsets, and then for each of the body delta pose, we're going to compute one limb new pose, check to see if this pose is actually possible with the leg. This is the step that we would fail on. If the check fails, we want to throw an exception from here and not continue on. While you're computing the corners, that's when you are doing the error check to see if this trajectory is possible. And throwing an exception is the best way to move up the channel. The fact that this poses for the body is not going to be possible, or at least not that particular pose. The upstream might do something different. Now, we're going to store the pose for the next iteration of the loop, because computing the new one new limb pose, as we remember, takes in the previous pose. That's how we get our moving cycle. So now, once we have all of the corners of the feet, we're going to do interpolation. So the interpolation will take in all of the feet tips, so these 12 positions for one given leg, and the number of interpolated points in between. So, the first thing that you do is you store the last corner as our previous corner for the algorithm. We then enter a for loop for each corners in the trajectory, so each of these 12. We get a new tip from the list. We take the previous one that we just set for the first loop, but will be set at the end of the algorithm, and invert it. The inversion of the previous tip is then multiplied times the new tip, and that will produce a delta. So this delta, if you multiply it times previous, will produce the new tip. Now this is cool because we can scale delta from 0 to 1, and that as we scale it, it will be multiplied times previous to give the motion from previous to new tip. Transforms are kind of cool. Ooh. For each interpolated point, we're going to scale the delta by the interpolation from 0 to 1, then take the previous and multiply it times this new scaled delta. Add this point to our list, and then set our previous point to the new point after the for loop is over. And that's how we interpolate between 2 points. So let's see what that looks like. Compute our tips with interpolation. We capture our previous. we compute a new tip, invert the previous, and iterate from 0 to 1 by the number of points. And we just multiply previous times the delta scaled by our scaling factor, j. Cool. All right. Next up, we're going to generate our leg trajectory plan. So this is the step at which we're going to compute every single point for every single limb, all the intermediate points in between 1 and 2, all the interpolated points for each of the legs before anything moves. So that's why we make the body plan, and then for each leg, we compute the foot corners and the interpolation. Now, if this fails, we want this function to throw an exception and move back up the line. We're not going to apply these interpolations. We're just generating all of the points for one entire body motion for all the legs. We're then going to return our hash map of tip trajectories. All right, let's see what that looks like. So we generate our plan. We start by making the cycle, compute our feet corners, compute our tips, and then add the tips to the leg map. By this point, with all of our helper functions, this should be fairly simple. Now that we have the ability to generate a trajectory plan and know if that trajectory plan is achievable, we're ready to implement our blocking version of drive arc. Now this is going to take in the cat, the body delta, and the amount of time we want this body delta to take. So the first step that we take when receiving this information is we're going to recurse this function until the minimum time is satisfied. And that means that we can't take anything less than one step, and one step should take a known amount of time. In our case, we're going to say about 250 milliseconds is the minimum time that one step cycle should take, and we're not going to take anything less than one step. So if the command requires that we either move too fast or that we take a step that's impossible, this is going to figure out for us, given the speed based on the body delta and the seconds, whether or not we can take one step. So we're just going to recurse and make sure that that time is big enough. And the way we implement that recursion is we simply, let's take a look here. So if the seconds equals 0, we set it to the minimum time, and we assume that 0 means the user doesn't care how long it takes. Next, we're going to say if the seconds is less than our maximum loop time, which is set to 25 milliseconds here, or 250 milliseconds, we're going to take the body, multiply it times itself, and the seconds plus seconds. And that way, drive arc will recurse until the minimum number of seconds is satisfied. All right. Next step, we're going to generate the leg plan and keep track of the number of steps. So every time we generate a plan, if it fails, we divide it by the number of steps, and we try a smaller version of the T delta body. So this is where we're actually going to compute the number of steps. And the way that works is we start with a for loop instead of a while loop. And this is just to make sure that it exits at some point. This number 100 is arbitrary. You could make that bigger if you'd be willing to wait for a longer period of time to compute a longer step plan. But if it fails out here, we'll have another layer above this to scale down our transform and try again. So 100 as an arbitrary number is perfectly fine at this point. Now we're going to compute our limb plan. We're going to check inside this function. It's going to do the checking, and it's going to throw an exception if any of the limbs cannot achieve the specific transform that we've given it. And if it does, we say the number of steps is how many we're going to use. And as you can see here, we've taken our transform and scaled it by 1 over the number of steps. Now the final check is to make sure that if the maximum loop time times the number of steps is greater than the seconds provided, then we know that the commanded speed is impossible and we return as a failure. All right. Shrink that back down. And back over here. So now we've gotten to this point where we've computed all of our tip trajectories for all of our limbs, and we know how many steps we need to go through to make it happen. Now, we begin our main iteration where we actually set the feet and wait. So, for each step, for each point on the trajectory, we then do for each leg inside of that, we're going to check to see if it's the A or B group and adjust the index accordingly. And we are going to set one foot position for each of the legs, and then inside this for each point loop, we're going to wait. So let's see what that looks like. For each step, for each point, for each leg, we check, is it in the B group? And if it is, we add the number of points divided by 2. And if index is greater than or equal to the number of points, we subtract the number of points, basically implementing this like a rolling buffer. We then actually get the appropriate tip out of the array. Note that we couldn't do this simply by iterating over this because we're computing an index and deciding which index to apply to which leg. We check to see that the tip is possible, and if it is, we apply it to the robot. And then once all of the legs have gotten their new tips, we wait for the computed amount of time for each leg. Then finally, once we're done with all of the stepping, we set the feet to the first index in the plan. And that means that each of the feet should go to their home locations. And that's just grabbing the leg map and grabbing index 0 out of the leg map to set for each leg. Pretty cool. So now, let's see what this looks like. So if you give a transform of 500 millimeters instead of failing, the recursion and the step calculation will figure out how many steps it needs to take. And you can see here it took 9 steps. And if you set that to 5 seconds, you should see stepping roughly at 0.1 meters per second, which is the rate at which we expect our cats to be walking for our final demo. All right. That's it for this video. Thank you for watching.